All right, got a lot of questions this morning, so I'll go ahead and address the one that was in the chat. If there is a chiral center and a chiral center is not created after going through Sn1, we don't need to specify the wedges or dashes. If you go through the mechanism and you end up losing a chiral center, then yes. If it's not chiral, you don't need to specify wedges or dashes. So particularly if we start seeing carbocation rearrangement, like we go from like a secondary to a tertiary, that'll be a lot of the times where you see these chiral centers destroyed. That's another issue with these Sn1 mechanisms, is that Sn1 has a trabit of, because you pay a lot of money to get chiral compounds, or enantiomerically pure chiral compounds, you run it through an Sn1 mechanism, you're probably going to lose that chiral center. With E1 reactions, is trans more stable than cis? In general, yes, and we'll talk about this actually the next test. There is a reason why cis can be more stable than trans. But generally speaking, when we're talking about linear alkanes, the trans is more stable than the cis, because if you were to look down that double bond, it keeps the biggest groups opposite each other, so they're anti. So if we were to do like a Newman projection, they would look anti under the Newman projection. Basically, it gets rid of a lot of the steric strain. So a lot of emails. I'll start working through them. First one, you can go through questions 59, 60, 61, and 62 on the homework. So question 59, solvolysis of tert-butyl bromide and methyl, and arrange the correct mechanism for its formation. So solvolysis here is when your solvent is actually part of the reaction. And this is kind of handy to have if you can make it happen, because if your solvent is actually a fair amount of the molecules that are in any type of solution. So if the solvent is the reactant, you're typically going to drive the reaction pretty quickly. But we've got tert-butyl bromide, and we've got methanol. So what will happen here is that we'll get a lone pair attack from the methanol onto the bromide, and this should break the carbon-bromine bond. Oops. And if we're going to the Sn2 pathway, this is what we'll end up getting. So let me see. Now, what will further happen, because we've got this hydrogen attached, we'll have the solvent acting as its own nucleophile. So methanol molecule will extract the hydrogen from this oxygen, and we'll end up getting methyl tert-butyl ether. So first question is, draw the structure and draw the product that is formed. The product that is formed here is methyl tert-butyl ether. So we've got a methyl group, we've got a tert-butyl group, and an oxygen between them. Come on. So first question can basically, what does it make? I'll switch to the desktop. We go to the methyl tert-butyl ether here. Next choice is A to B, the correct order of the mechanism. So the first thing we're going to do, looks like it's suggesting that this is going to go through an Sn1 pathway. That's fine. What we end up doing is breaking that carbon-bromine bond. So that's the first step. Your second step here is nucleophilic attack of the methanol onto the carbocation. So this lone pair is going to act like a Lewis base. And then your last step here is that we're going to have another solvent molecule of methanol attack the hydrogen that's on the methanol that attacked the tert-butyl ether, or methyl tert-butyl ether, and this will end up giving us our final product. Now, what I don't like about the implications of these types of mechanisms, and it does end up kind of being a bit of a contradiction if you dig too deep into it, is that methanol here is not a fantastic base. It's a much better acid than it is a base. That seems kind of contradictory. And really what you have going on is you're forming HBr, and the hydrogen bromide is here. This is really an equilibrium-driven reaction. And so we have the methanol and the terpbutyl ether going back and forth to HBr and the methyl terpbutyl ether. Because this is the solvent, it's in such high concentrations, it's going to drive this reaction forward and pretty much guarantee that this is all we're producing. But I don't like this product. That's what the mechanism suggests, and the reason I like it is that methanol is really not that good of a base. Really what you probably have is trace amounts of HBr that are being formed, but that's kind of beside the point. Just something to keep in mind with mechanisms. They're a way of understanding the reaction. They may not necessarily represent reality. All right, question 60. Write the chemical equation clearly showing the stereochemistry of the starting molecule in the product for the reaction of S1-bromo-2-methylbutane with sodium iodide and acetone. Be sure to answer all the following parts. So the first thing you need to draw is one bromo 2-methylbutane. And we're looking for the S conformation with this methyl group. Since we've only got one chiral center, it's not going to be the first one, it's going to be the methyl group. Let's see here, we've got, if we draw the methyl here, carbon, 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 so that's 1, 2, 3. If we draw a wedge, see here, 1, 2, 3, that's S. We want the S, so we're going to want this to be wedged. So that is your S1-bromo-methylbutane. We're going to do sodium iodide here. Since it's only one product, which makes sense, we're going to get substitution of the bromine. Again, it says a single product. You can imply from the fact that there's a single product, this has to be an Sn2 pathway. Another thing, acetone isn't a protic solvent. So if you look up dielectric constant, it's also not that great of a dielectric constant. But again, you can kind of infer from this that they're saying it's an Sn2 mechanism because there's only one product. If it went through an Sn1 mechanism, we'd have a carbocation here. It would shift here to give us a tertiary, and we end up with two products, both the R and the S. So when we do the substitution, we should end up with the 1-iodo 2-methylbutane in the S conformation. So let me switch to the desktop. And that's correct. So what's the conformation of the product? Because this is an Sn2 mechanism and we're not changing the stereochemistry here, we're going to preserve it as the S. There you go. Question 61. Draw the structures including the stereochemistry of compounds A and B in the following sequence of events. So we have, I'm not drawing this out. I'll leave that to you to draw it in the program. I remember doing this problem one time. So you've got your cyclohexane, and you've got a big bulky terpbutyl group and an alcohol. These are going to be trans to one another if you draw the compound. Actually, I think with this you can get away with just doing this, the drawings. You don't need to work with this particular cyclohexane. Sorry, hold on. And this compound you've actually got over here, this is tausyl chloride. So that SO2Cl2, that it is para-nitro, yeah, like that's tausyl chloride. So compound A here is the tausyl complex. And it's going to make you draw out everything. So this TS here is an SO2, benzene ring, and O2. So the first product here is just the tosyl complex, the lithium bromide. This is going to go through an Sn2 pathway. In order to get rid of the tosyl group, basically it's going to invert the symmetry. So when you finish this reaction, it's lithium bromide. Instead of being equatorial, it's going to be axial. So we've got a methyl group here. The bromine's going to hit it here. That's going to push the methyl group down, displace the tosyl group, and so you end up getting bromine in the axial position. Now again, it is a lot of work to draw that. I'm not going to draw it, but I think you get the big picture here. That big benzene ring it's showing you, that's tosyl chloride. Question 6.2, reaction of ethyl iodide with triethylamine yields a crystalline compound with formula C8H20Ni in high yield. This compound is soluble in polar solvents such as water, but insoluble in nonpolar ones such as diethyl ether. It does not melt below 200 degrees. Draw a reasonable structure for this product. Click on the draw structure to figure out what to... Okay. So the reason they're giving you this hint about the diethyl ether, this is an ionic complex. And so we have ethyl iodide with triethylamine. So what will happen here is we'll have nitrogen attack on the iodine. This will displace the iodine, and we'll get nitrogen here with 4 ethyl groups on it, and iodide. So you'll end up with the, and that's where your C8H20 comes from. When you add all these up, that's 2, 4, 6, 8 carbons. You'll get the 20 hydrogens when you add up the hydrogens here, and then your N and your I. So what you have here, and this is a pretty common reaction with amines, the lone pair will displace the halogen, and you'll end up forming what's called a tertiary or quaternary ammonium salt. All right, so that's that question. Can you go over the last 2 pages of the packets on 23, 24? So let me bring up the packets. All right, this one can actually be done in 1 step. And what I recommend is just sodium metal. So what will happen with sodium metal here, this is a reaction that we cover in the lab this week. The sodium reacts off the hydrogen and you end up generating your alkoxide. And with this you get what's referred to as an intermolecular reaction. So the oxygen here will attack the carbon that binds the chlorine, will break the carbon-chlorine bond, and what we'll end up getting is this ring. And Cl- will get sodium chloride. So this can all be done in 1 simple step. Hit it with a hydrogen, and basically what you're doing is you're taking one in the molecule and making it your nucleophile. So this is your X- in the reactions of alkyl halides with a nucleophile. Your nucleophile is just part of the molecule. 6-member rings are super stable. They're very easy to, that's why they're so easy to generate. And we displace the chloride. Now, page 24 is pretty much the exact same reaction. That's one of your options here, is that the isopropoxide can remove a hydrogen off of this and you can generate this product here. But your isopropoxide isopropanol can also do elimination reactions. And so, what can you eliminate? There's actually a lot of solutions to this. We can eliminate the chloride. We can eliminate the we can eliminate the alcohol through a base catalyzed dehydration. We can eliminate both. Now the thing here is that if you look at your carbon-13 NMR, there are 4 chemical shifts. Total area here is 7. So if you look at the starting compound, there are 7 carbons in this, so which means that you're not doing any type of carbon elimination. So what we're looking for is something that has 7 carbons in it. That's going to be all of these. But here's the thing is that you see area of 2, 2, 2, and 1. This implies a mirror plane. So if we look at this molecule, there's no mirror plane. So there's 1, 2, 3, 4, 5, 6, 7 carbons, 7 NMR peaks. This won't work. 1, 2, 3, 4, 5, 6, 7. 7 carbon peaks. In the NMR, that won't work. This has a mirror plane. So 1, 2, 3, 4 carbons in the NMR. This has a mirror plane. 1, 2, 3, 4. Excuse me. So now the question is, based on what we see in the NMR data, do we expect it to be this compound or this compound? Well, if we look at this one, these are all CH2, CH3, CH groups. So we're expecting the chemical shift here between 0 and 50, but we see a shift at 131 and 125.7. That's a lot more consistent with alkenes. So if you look at the tables of carbon-13 NMR chemical shifts, which you get provided on test, you'll see that these are actually a lot more consistent with that 131 and 125 peak. And then your 16.5 is going to be this one, and your 27.9 is going to be this one. And this is actually pretty common with chemical synthesis, is that you kind of have to make a list of what you think are the likely products from most likely to least likely, and then try to figure out which of these compounds you actually generated based on the results of your chemical analysis. So next question, can you explain the IR of alcohols, the broadness of the peaks between alcohols and strong hydrogen bonding versus weak? The NMR both groups as well. So we'll do the NMR first, and there's an aspect of the NMR that kind of leads into the IR. So with the NMR, and I'm guessing the question here really refers to the 1H NMR. So the thing is that alcohols, generally speaking, participate in hydrogen bonding. We need to put the qualifier on there, generally participate. This isn't always true. When this R chain starts getting very big, they stop participating in hydrogen bonding. We'll get to why that's important in a minute. Because they participate in hydrogen bonding, what really happens between alcohol molecules in solution is that we temporarily form the alkoxide and the hydronium forms of the alcohol. Now, this isn't a huge amount, but the thing is that this is a dynamic equilibrium. It's constantly going on, and because of that, this H here doesn't do J coupling. So there's no J coupling with this H, it's always a singlet. And what we'll see in the 1H NMR, I think it's about 5 ppm, is we'll see a singlet, usually area of 1 corresponding to the alcohol. Now, these down here do participate in J coupling. So this will be a triplet, this will be a triplet plus a quartet, and this one will be a triplet. So what we'd expect to see beneath the 5 ppm in that 0 to 2,5 range is your triplet of quartets, and then another triplet. So with all alcohols, you typically see this singlet, roughly I think it's 5 ppm, you need to go check the tables, but about 5 ppm, and it's always a singlet because this hydrogen pops on and off so much it doesn't have time to do J coupling within the molecule. Now, this back and forth also gives rise to a peak in the IR, about 3,600 wave numbers. Now, what bothers me is that textbooks label this as the alcohol binning peak, and that's not what that is. So if you look at the IR of any alcohol, generally speaking, any alcohol. Again, if it's a long chain, you're not going to see this. And if you don't believe me, go look up 1-octanol on the NIST chemistry webbook. And you can see examples where this isn't true. But generally speaking, for small, fairly acidic alcohol groups, we get what's called the hydrogen bonding peak. And the reason why it is so broad is that this is going on. So it's not a very well-defined peak. Your CH3, CH2, CH groups, these are very well defined. Like, these bonds never make or break. Pretty much always tetrahedral geometry is associated with them. And because of this, we get very fine, very narrow, very specific sharp peaks that define the alkane bending modes. With alcohols, because the alcohols are all engaging with each other and sharing the hydrogen, you see a range of frequencies because sometimes they've just exchanged them so that OH bond is really strong. Sometimes they're in the process of exchanging them so that OH bond is weak. Sometimes the hydrogen is right between the two oxygens. So you end up generating this really broad peak. Now, the reason I say this is not an alcohol peak, this is a hydrogen bonding peak, is because amines do the same thing, and so do sulfides. So NH2 groups and SH groups also engage in hydrobonding to different degrees, but they engage in it. And so they all show this peak about 3,600 wave numbers. So with no context, the only thing you can say when you see this 3,600 wave number peak is that whatever the molecule is, it engages in hydrogen bonding. But if you have context and you know that the alcohol is the only possibility for a functional group that would participate in hydrogen bonding, again, you've got the NH2, SH, and OH. If you know the only possibility here is that you could form an OH, then you can use this as a diagnostic peak. And it's going to be a very big, very broad peak. Now, again, if you start looking at these super high chain alcohols like 1-octanol, what you'll see instead of this big broad peak is a very tiny blip at 3,600. And this is two effects. One is that these peaks are becoming so much of the spectrum that they're beginning to drown out the alcohol or the hydrogen bonding. The second is that the long chain alcohols aren't very good at hydrogen bonding. That OH group has so much electron density, it basically acts like it's a nonpolar bond, so you don't really see it. So generally speaking, I would sit back and say anything beyond like N-butane or N-pentane or N-butanol and N-pentanol, so 4 or 5 carbons, you're probably not going to see that 3,600 wave number bending mode anymore. So once you get beyond like 4, 5, 6 hydrogen carbons in your molecule, you probably can't use the 3,600 as diagnostic anymore. But definitely if it's less than 6 carbons, you're definitely going to see this 3,600 wave number. So hopefully that kind of helps you understand better how to use the IR. Again, we're not going to go with esoteric examples in this class. Generally speaking, if you know we're making alcohols, or you know an alcohol is a possibility and you see that big bending band at 3,600, and you'll have tables for this, you definitely have an alcohol present. Answer that question. Question 79 on the homework. Select the combination of alkyl bromide, potassium alkoxide that would be the most effective in the synthesis of the following ether and select the single best answer. So this is another one of those. The ether here, the alkoxide is your nucleophile, and you've got some alkyl halide that you're trying to displace to make the ether. So we've got some ROX minus that's supposed to be our nucleophile, and some R prime X that it's going to attack to give us our RO, R prime, X minus. Now, all alkoxides can participate in elimination reactions. They're kind of our ubiquitous example of it because they are fairly acidic. When we get to alkynes, we'll talk about better ones. But generally at this point, the alkoxide is the big one. So if you have the choice between a substitution, most likely it's going to be an Sn2 pathway or an E2 pathway. The only way to guarantee that this doesn't happen is to ensure that you don't have any hydrogens to eliminate. So if we know our product is an ROR prime, and this is what we're making is the methyl cyclopentyl ether, we have two places we can break it. We can make this the R prime and this the R, and so we end up with cyclopentoxide, and in this case the methyl bromide. Or we can break it the other way. We can make this the R prime and we can make this the R. So we end up with methoxide and bromocyclopentane. Which one makes more sense? Well, both will do this substitution reaction. So both are answers. They're not necessarily wrong answers, but the better answer is one that doesn't have the possibility for elimination. And the way we make that happen is we use the methyl bromide. So methyl bromide here has no hydrogens to eliminate. It has to undergo the substitution. And so if you look at the answers, the methyl bromide and potassium cyclopentoxide, that's the best answer. The 2-methyl cyclopentyl bromide and the potassium terbutoxide, those do not make this ether at all. And then there's the alternatives, bromocyclopentane with potassium methoxide. We wrote that one. It doesn't work. It doesn't work as well because you can do elimination. And the 1-methyl cyclopentyl bromide and potassium methoxide, if you write those out, cannot possibly make the ether you're trying to synthesize. All right, can you also go on page 13 of the packet, the third problem that uses HCl? So if you re-download the packets, so the packets were updated last week. That problem was eliminated, I think, because I'm not seeing HCl, I'm seeing H plus H2O. There was an earlier version that had the HCl. It had to be gotten rid of. Actually, I think it ended up being a lot more complicated than it looked. So if you re-download it and you don't see it, that's why. So go back and check to see if you're just working with an old packet. Packet questions. So, how is this octanol? So in one of the packet problems, you got this. And the question is, how is this octanol, not heptanol? Heptanol is 5 carbons, so 1, 2, 3, 4, 5. If you say heptanol, you kind of ignored this ethyl chain. This 1, 2, 3, 4, 5. That is heptanol. And then 4-heptanol doesn't actually make sense. So this would be 4-heptanol. It doesn't make sense because you're trying to minimize the numbering on the alcohol. So 4-heptanol is actually 2-heptanol, just numbered from the wrong end. So with alcohols, the alcohol does not designate the end of the parent chain. Typically what we're going to do with these is we're going to keep the parent chain, the alcohol on the parent chain. It gets a lot more complicated if the alcohol isn't on the parent chain. So with this, the longest chain here is octane, 2, 4, 6, 8. So that's where your octanol comes from. And we want to minimize the numbers. So 1, 2, 3, 4, octanol. And if you look at how is this octanol, again, there's another question that's being asked. Basically, it's this one, but now we've added branches. It's the same thing. It doesn't make sense to call this heptanol because then you'd be ignoring the other 3 carbons. So we don't name alcohols with this on the number 1 carbon. We look at the longest chain and then give the position of the alcohol. This one. So looking for the longest chain, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. That might be a one that's actually done incorrectly. That's actually kind of a tricky one. I think it's it's one of those ones that was probably written out with the best of intentions. I'm going to go with what the key has, but you are correct that this is kind of weird. You wouldn't... So the way the key was written, and actually this is kind of a bad example for this, is they're defining this as the parent chain. So 1, 2, 3, 4, 5. There's your pentanol. And it's a 1 pentanol. And then your branches, you've got a propyl and a methyl. So 2 propyl and 3 methyl. So that's for the 3 methyl. And again, the alcohol here is going to set the primary carbon. The alcohol has to be closest to the end of the chain. So that ends up giving you 1, 2, 3. So there's your 2 propyl and 3 methyl. So the next one. Branched alkyl halides. 2, 4, 6. So again, what you're looking for is the longest chain. So we have 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Doesn't really change anything. And so this is where your hexane comes from. And then we've got iodo and methyl. The goal here is to minimize the number from the starting one. So if we do 1, 2, 3, 4 versus 1, 2, 3, this will be 3 iodo, 4, 5 methyl. There are people that argue the sum should add up. So if you reverse this, you'd have 2 methyl, 4 iodo. This would give you 6 versus 8. I have never seen a single textbook say that. I think this is just kind of like, what's a good euphemism for kind of a folk tale? But I have seen people swear online that you have to do this way the sum of the numbers is minimized. Again, I've read about 4 textbooks on this. Not a single one has ever made that claim. Always minimize the front number. Every single one has said minimize the first difference. So that's where the hexane comes from. And then another question. Does the numbering start below the alcohol? So then we've got a similar one where we got an alcohol tacked onto it. So we have 1, 2, 3, 4, 5. So we've got a pentanol. And it's going to be the first one. And then we've got iodo methyl. So 2 iodo, 4 methyl. Now again, the alcohol is always given the priority in the naming over alcohol, over alkanes and alkyl halides. The reason being is that this is the most reactive. So in terms of chemistry, this is why we name them pentanol, is to indicate that the alcohol is the most reactive function group. This isn't always true. If we had an aldehyde in here, this would end up actually being pentanal. And we would have 5-hydroxy, 4-iodo, 2-methyl, pentanal. The reason being that the aldehyde is a lot more reactive than the alcohol. So this is why the alcohol gets its numbering first, is that it's the most important functional group in terms of this molecule. Now, again, we're always going to have our examples where the alcohol is on the longest parent chain. So we identify the longest parent chain, and we're going to number it in such a way that the alcohol is minimized. So if it was here, it would be 2. If it was here, it would be 3. It was here, and then we'd start the counting from the other end to make this 2. If we put the alcohol down here, it would start the counting down there as well. So when it comes to alcohols, the goal here is to minimize its number because it's the one that's going to react first and react the strongest. So we give it the priority with the naming. As far as practice go, would you mind doing an example on the test packet? I did one at the start for the carbon-13. In terms of how you go about those problems, come up with every conceivable reaction you can think of. That's kind of why it's given there, is to see what you can remember from in terms how you apply the basic reaction. So what's a reaction of an alkoxide do? It can do elimination, it can do substitution. You have the previous problem on the previous page where you can actually do a ring closing. That's how you approach those problems, is come up with a myriad of possibilities, because a lot of these reagents can do a lot of different reactions. Write them all out, and then based on the NMR, see which of the molecules you generate is consistent with the final answer, or consistent with the spectrum. Questions pages 16 through 18 on the packets. So, solvent effects on reactions. So what this is trying to do is test your understanding of, do you understand how the solvent affects a reaction? And this goes back to a diagram I drew in an earlier live stream. When it comes to your nucleophile, if you have a strong base, you're going to draw towards elimination. So these are strong bases. So you can get elimination. If you just have weak bases, you're going to get substitution. The 1 versus 2 mechanism, so the bimolecular versus the unimolecular. Bimolecular requires a low dielectric constant solvent, preferably one that's aprotic. The unimolecular mechanism, high dielectric constant, protic. So for all of these examples, the nucleophile isn't changing between the examples. This is HCl, and it's doing substitution. So we're always on this end of the spectrum. The question is, are we doing a bimolecular or a unimolecular mechanism? Because there are implications about the final product. So they're the same as alcohol, so we're not changing anything about primary versus secondary. And we're replacing it with chloride. So if we go through an Sn1 pathway, we're going to start with a carbocation. And what will happen is that we'll get rearrangement to move it toward the tertiary. And now when the HCl attaches, we get a tertiary chloride. So that's if we go through an Sn1 pathway. If we go through an Sn2 pathway, will end up just replacing the alcohol. No, I'm sorry. Let's see that, OH. Yeah, so for the Sn1 pathway, we'll end up taking the alcohol off. We'll get a positive carbocation, but it's primary. Through a hydride shift, we'll end up getting it to a tertiary, and we'll put the chloride on the tertiary. If we go through an Sn2 pathway, we substitute the alcohol off directly. And so we end up with a primary chloride. So the question is, what's the difference between Sn1 and Sn2? And here are the issues of the solvent. So if you look at dimethyl sulfoxide, DMSO, this is a dielectric constant, I think, of like 78. This is a super high dielectric constant. It's actually better than water at stabilizing carbocations. So for the DMSO, we're going through an Sn1 pathway. Your THF in this case actually has a tiny dielectric constant, it's less than 10. It can't stabilize carbocations, so this is going to drive us to the Sn2 pathway. And you see this on subsequent page. We have a strong base tert butoxide in THF versus a strong base tert buton, or this is isopropoxide in DSO versus THF, and we've got a bromine. Both of these are going to do elimination. This is definitely elimination through a large bulky base. But in terms of THF, we're not going to get carbocation rearrangement. So if you get rid of that bromine through an E1 mechanism, which you're going to do with the DMSO, you're going to get carbocation rearrangement from that primary carbon, move it down one carbon to get you to a tertiary carbocation, and then you can do elimination between the 4 methyl groups. If you do it through THF, you can't form the carbocation, so you have to eliminate that bromine directly, which means that you're going to end up getting a terminal alkene, that double bond from the methyl group, from that group that bromine is attached to the adjacent carbon. So that's the way you approach these, that you look at the solvents and say to yourself, okay, is this going to favor the Sn1 pathway or the Sn2 pathway or the E1 pathway or the E2 pathway? And so that's finally it for all the questions I got asked this morning. At least by email. I haven't actually checked the chat menu in a bit. Will we still be meeting at the same room again for the exam? I need to send an email out this morning just to make sure. I want to check the room before I send it out, but I'll send you an email. I don't think it's the same room. So that's why I need to check. But yeah, I'm going to send out an email after I get out of live stream today saying what the room is. Yes, if you're taking organic, you got your exam this week. It is during the lab period, so all A and B groups have to show up to the classroom. We'll take the exam for an hour, and then if you're in the A group, you get to go home. If you're in the B group, then we're going to go to lab. Lab today is a qualitative lab. You're not doing any calculations in the lab, so it is going to take you that full block of time to complete it, but you don't have to do anything before you leave. Just run it, clean up, and then you're free to head out. All right, so I'm not seeing any questions being posted to the chat. So again, I'm here. These are office hours. These aren't lessons. These are lectures. But again, please feel free to post anything. And yeah, I'm just going to get a little bit of work done. Right, so that's it for the line of shooting today. Again, if you've got questions, please feel free to email them in advance, and I will talk to you all tomorrow.